here's the setting. Remember, the SKs are all the KY's intersection probabilities summed, K running from 1 through n. The inclusion-exclusion principle tells us I can get the probability of a union, a disjunction, by adding and subtracting these terms one at a time. Now, I'm going to remind you of an old principle, and this is going to engender for us a completely new and very useful vantage point. So, to do this, let me introduce just a smidgen of notation. Remember that in the context of sieves, I talked about the events A1, A2 through AN as bad events. Of course, this is just to lend color to our problem, which would otherwise be drab and algebraic. So, bad events occur if any of the A's occur. Let's introduce some notation to capture the occurrence of a bad event. So, for an index j running from 1 through n, let x sub j be a variable which takes a value 1 if the bad event aj occurs and is 0 otherwise. In other words, the value of xj is a flag, is an indicator for whether the bad event aj occurred. Now, this is promising because the moment I give you nomenclature and notation like this, that should tug maybe a faint atavistic thread in your memory. Where have I seen things like this before? Of course, xj is a chance variable. It depends upon the performance of the underlying experiment and whether the chance outcome is in aj or not. But xj at heart is a coin toss. It's a 1-0 variable. xj is a Bernoulli trial. Now, what's complicating matters here is that as you let j run through the indices 1 through n, then the values x1, x2, x3 through xn, the indicators for whether the bad events 1 through n occurred, are not necessarily independent. If they were, we'd have the familiar setting of repeated tosses of a coin. Now we have tosses of a coin, but the tosses could depend on previous tosses. Dependency is baked into the cake here. But nonetheless, our experience of coin tosses says, well, it was very profitable to look at the accumulated sum, the accumulated number of successes of these coin tosses. Let's do so without any further ado. Suppose we add the indicators x1 through xn. I would love to give this sum a name, S, but S is already spoken for. We used SK for these sums of these conjunction probabilities. So let's introduce a new notation. Let's call this partial sum of x1 through xn M sub n. This stands for the accumulated sum of these indicators. In words, Mn tells us how many of the bad events occurred when the experiment was performed. Excellent. Now we've just recast the problem in a new light. A little smidgen of extra notation, if you will humor me, was going to simplify all our equations and make them look very, very symmetric. Sk was defined at the top of your screen as a sum of conjunction probabilities k at a time. K ran from 1 through n. It'll be awfully convenient if we introduce some notation for the case k equal to 0, and here it is. As a matter of definition, let's define S sub 0 to be 1. Now, with this in hand, let's go and take a look at our inclusion-exclusion principle. And now, let's recast it in a very general light. So, the inclusion-exclusion principle, the probability of the union, tells us about the probability of anything bad happening. The probability of nothing bad happening is clearly the obverse or the complement of this, and therefore the probability of the intersection of the complements of all these events, the probability that no bad event occurs, that only good events occur, is 1 minus the probability that any bad event occurs. Of course, this is simply additivity. We partition the space into two pieces, a bad union and its complement, a good intersection. For the probability of the union, the baby version of the inclusion-exclusion principle tells us we've got an alternating sum in S1 minus S2 plus S3 and so on. Now, in front I've got a 1. Well, we can identify that with S0 per our definition. And then I subtract my alternating sum S1, S2, S3. So what have I done? I started with S0, then I have to subtract S1, and now the sign of S2 flips and it becomes adding S2, and then the sign of S3 flips, it becomes subtracting S3, and so on down. And the last term becomes minus 1 to the power n Sn, and so now we've got a fairly elegant, at least easy to remember formulation for the probability that no bad event occurs. It's written as S0 minus S1 plus S2 and so on. Remember, S0, just by definition, was 1. But the probability of no bad event occurring, this could be identified with the probability in terms of our accumulated sum of indicators. This is the probability that the accumulated sum of indicators is 0. No bad event occurs. In other words, what we've computed is the probability of an atom for m sub n. We said the probability that m sub n is 0, that no bad events occur, is given by this alternating sum starting at 1. S0 is 1 minus S1 plus S2 and so forth. And this opens a door for a generalization which is quite powerful. It was unlooked for. Remember, originally we were just talking about unions, conjunctions and disjunctions. But now we realize at the heart of it is also a counting element. We are counting how many bad events occur. Of course, it would be ideal if none occurred, but in the context of rare events, we should always draw the distinction clearly between implausible and impossible. It is implausible that a rare event occurs, but it is not impossible. Then the question is, how many of these bad events occurred? We are now prepared. Our inclusion-exclusion principle, the baby version, tells us in the simplest form that the probability of no bad events occurring is given by an alternating sum. It should come as no great surprise that in general now we've got an alternating form for the probability of a certain number of bad events occurring. What is the probability that exactly k bad events occur? It doesn't matter which k, but some k occurred. What's the probability of that? Again, we are going to have an alternating formulation involving these s's. Remember, what were the s's? They represented sums of conjunction probabilities. If we expand out such a sum, for example, on the right, what is the very first term? Well, j is 0. If j is 0, then we have k choose k times sk with a positive sign in front because we have minus 1 to the power 0. What if j is 1? Then you have minus 1 to the power 1, which gives you a negative sign. And then you have k plus 1 choose k times s of k plus 1, the sum of all intersection probabilities, k plus 1 at a time. Next term, j equal to 2, well, minus 1 to the power 2 is plus 1. Then you have k plus 2, choose k. And then you have sk plus 2, the sum of all k plus 2y's intersection probabilities. And so on down. Okay, this is now the industrial strength version of the inclusion-exclusion theorem. And I have not made clear yet that whether or how this connects to this idea of a metaphorical sieve. Right now we are building background. But we can see some tenuous connections. The sieve dealt with probabilities of unions, or equivalently, the probability of the intersections of complements. These sums of these indicators, these bad indicators, tell us something about how many of these rare or bad events occur. And so, in this inclusion-exclusion principle seems folded in a strategy for creating a metaphorical probability sieve. to try to sieve out the bad events from the ensemble. Right? So let's begin first by providing an elementary proof of this principle. And to do so, there are several approaches, but to do so, I'll pick one which appeals to me by appealing to a principle from magic.